Hi guys, my name is IBM and today I'm trying to solve May June 2022 paper 2-1, and without wasting time I would like to take you to the question papers. Do not forget to subscribe, share the videos. You can also check out the topical past paper questions in the previous videos so that you get more confidence in every topic of AS and A level. So without wasting time, I would like to take you to the question paper. So this is May, June 2022, and this is paper 2-1. A friend of mine in Pakistan told me to record all the 2022 papers because he found a lot of challenges in most of them. That's why I'm recording them now. So without wasting time, we shall go to question number 1. So define velocity. So of course, we know that velocity is equal to the change in displacement divided by t. So I will simply say velocity is the rate of change, the rate of change of displacement. The rate of change of displacement. So it's wrong to say velocity is displacement over time. The word change is very important in the definition of velocity, because if the displacement is not changing, then we don't have velocity. So velocity is the rate of change of displacement. Or you can write simply a simple formula: change in displacement, this divided by the time taken. So that would be velocity. Always remember to put a change in the definition of velocity. It would be the same with acceleration. You must put change in velocity for acceleration. So a rock of mass 7.5 kilograms is projected vertically upwards from the surface of a planet. The rock leaves the surface of the planet with a speed of 4 meters per second at time t equals to 0. The variation with the time t of the velocity v of the rock is shown. So this graph shows the variation of time, variation of velocity with time. So assume that the planet does not have an atmosphere. If it doesn't have an atmosphere, automatically we shall assume that the acceleration, there's no air resistance. So it means acceleration due to gravitational field strength G is going to be a constant. If it has no atmosphere, gravitational field strength is a constant, which can also be seen from the graph that is a straight line, which means a constant gradient. So the acceleration due to gravity on that planet is constant. Determine the height of the rock above the surface of the planet at t equals to 4 seconds. So let's say at from t equals to 0 to t equals to 2.5, it is going upwards, because we see that the velocity is decreasing, so it is going upwards. So here it has reached maximum velocity, that is 2.5 seconds. This was t equals 2.5, this is t equals to 0, it is leaving this point here. So here velocity is 0, and here velocity was 4 meters per second. Then after 2.5 seconds, there is a change in direction, so it is falling downwards. So after 2.5 seconds, it's falling downwards, and the velocity with which it hits the point is this one here, which is I think that is negative 2.1 divided by 5, that is 0. I think 0.2, so this will be 2.4. So when it reaches here, it is 2.4. It is a velocity of 2.4 meters per second. So we want the height, this height here, this height above the surface of the planet, assuming that this was the surface of the planet. So to find the distance going upwards, I'll find the area under this part of the graph. And find the distance when it is going downwards, I'll find the area under this part of the graph. These two are in opposite directions, so if I'm finding displacement, I'm going to add it. One will be positive, one will be negative, which is as easy as subtracting. So I'll tell the examiner that displacement equals to the area displacement equals to the area under the graph. So it means the height we are looking for above the planet is actually the displacement. The area of the first part is a triangle, so it will be a half times what will be the base will be 2.5. This is 2.5 seconds. Then times what will be like the vertical height is 4 meters. 4 meters per second. Then this is the distance upwards. So I will say plus negative. So I'll just say minus the distance downwards. So the distance it falls downwards is going to also be the area of a triangle, which is a half. What will be like the base is going to be 4. This distance here is 4 minus 2.5, which is 1.5. So this is going to be times 1.5 times this distance here, which is actually 2.5. But remember, this was seconds. I have to put units there so that people will see that the answer is in meters. So this is seconds, then times 2.4 meters per second. So you will notice that the seconds have cancelled out. The seconds have cancelled out, so we remain with only meters. So precisely we have 2 times 2.5, which is actually 5.0, minus, here we have 1.5 times 2.4 divided by 2, which is 1.8, so minus 1.8. So I'll just subtract 5 minus the answer, which is 3.2. So this is going to be 3.2. So I'll write here 3.2 meters above the planet. Then determine the change in the momentum of the rock from t equals to 0 to t equals to 4 seconds. First of all, always make it a point or a habit to write the formula before you substitute, so that in case you make a mistake in substitution, you still have a mark for writing the formula. So momentum is going to be equal to mass times velocity. And we know that the change in momentum will be equal to the mass times actually the change in velocity. So the mass is 7.5, then velocity changes from 4 meters per second to negative 2.4. And the change means subtracting, but again the velocity is going to be negative, so we shall have a positive value. So you may decide to make the initial, you start with the initial velocity minus the negative of the final velocity, or the reverse. Final velocity minus initial velocity, the order doesn't matter. You just need a change to get the magnitude of, So this is going to be the mass, which is 7.5, into brackets, change in velocity, the initial velocity is 4.0 minus negative 2.4. So this is going to give me the change in momentum, which is 7.5 into brackets 4 plus 2.4, which is 48. So this is going to be 48. Either you get negative 48, is it 48? Yes, this is negative, either negative 48 or positive 48. It will depend on which one you consider the first velocity. Alternatively, you might have done 7.5 into minus 2.4, then minus 4.0. That is still a change in momentum. This would give you negative 48 Newton seconds. So either you have a negative or a positive. That is, as long as it is a change in momentum. Then determine the weight of the rock on the planet. Of course, since there is no atmosphere, we don't expect air resistance on the block. So if it is falling, it is only falling due to its weight. So the resultant force on the block is going to be the same as the weight. So the resultant force, the weight, W, is going to be the same as the resultant force on the rock. But of course, you remember, according to Newton's second law, the resultant force is equal to the rate of change of momentum. So this is going to be equal to the change in momentum over time. That is the resultant force. So this is going to be 4/8 over the time, which the time is 4 seconds. So this momentum changes over a time of 4 seconds. So this is going to be 4 over 4 seconds. So I'll just press my calculator. 48 divided by 4, and I get 12. So the weight is going to be 12 newtons. Alternatively, you can use W is equal to the mass times acceleration due to gravity, which will be the mass. To find the acceleration, you can find the gradient of the line, or you can get final velocity minus initial velocity over time. So this would be 7.5 times final velocity could be negative. You could say negative, or I can just reverse the velocity so that my answer is finally positive. So I can say 4 minus negative 2.4, then divide by the time, which is 4.0. And of course, I know this still gives you 48 over 4, which is still 12 newtons. Okay, so the answer is 12. I know you may calculate and get negative if you reverse the velocity, but still they will not penalize you for negative. So in practice, the planet in B does have an atmosphere in practice. So that one, the first scenario was theoretical. That causes a viscous force to act on the moving rock. State and explain the variation, if any, in the resultant force acting on the rock as it moves vertically upwards. So we are considering the rock moving vertically upwards. This is direction of motion. So its weight is acting vertically downwards, so that is W. Because it's moving vertically upwards and there's an atmosphere, it means the force due to air resistance is downwards. So the resultant force is equal to the weight plus the force due to air resistance, which is downwards. So the resultant force is downwards and is in the opposite direction to motion. That means, and remember, as it moves upwards, force due to air resistance, of course, the speed decreases, which means the force due to air resistance also decreases. So the viscous drag or the force due to air resistance decreases, but remember the weight is constant. What happens to the resultant force? Remember, the resultant force is the weight plus the force due to air resistance. As it moves upwards against gravity, it slows down. And remember, the viscous drag or the force due to air resistance depends on the speed. So this decreases. So this means the resultant force is also going to be a smaller value. It is going to decrease. The resultant force F, which is in the opposite direction to motion, is going to decrease. So the question is, state and explain the variation, if any, in the resultant force acting on the rock as it moves vertically upwards. So number one, moving vertically upwards, the speed decreases. The speed decreases. And if the speed decreases, it means the viscous force also decreases because it depends on the speed. So the viscous force decreases. And if the viscous force decreases, remember the weight is constant, and the weight is constant. So if the viscous drag of viscous force decreases and the weight is constant, it means the resultant force decreases. So I don't want someone to write me a message and ask, why does the viscous force decrease? Imagine you are in a car and you put your hand outside through the window. Before the car starts moving, you don't feel wind blowing, but as the car starts moving, you feel wind blowing your hand, and if the car speeds up, you feel the wind blowing you even more. If the car slows down, you now feel less wind blowing the hand, which means viscous force, which is like friction. In this case, it would be air resistance. is also depending on the speed of the moving object. So here the resultant force decreases. Question number 2, state what is meant by center of gravity of an object. So the center of gravity is a point where all the weight of the object is considered to act. So there's always a point where all the weight of the object is considered to act or is taken to act. And whenever the object is suspended at that point, it remains in equilibrium. So that is what we call the center of gravity. A non-uniform rod XY is pivoted at point P, as shown in the figure. The rod has length 4 meters. It is non-uniform, I think. The rod has length of 4 meters. The center of gravity of the rod is 1.7 meters from end X of the rod. Point P is 1.1 meter from end X. A sphere hangs by a wire from end Y of the rod. The weight of the sphere is 3 newtons. The weight of the wire is negligible. A force F is applied vertically downwards at end X so that the horizontal rod is in equilibrium. So it is in equilibrium. They are applying a force F at end X so that the horizontal rod is in equilibrium. By taking moments about P, calculate F. So we're taking moments about P. So F is pulling the rod in this direction, so it is anti-clockwise. And the weight of the rod is pulling the rod in that direction, which is clockwise. Then the sphere is also pulling the rod in that direction, which is clockwise. So the sum of clockwise moments should be called the sum of anti-clockwise moments. So for equilibrium, the sum of clockwise moments should be equal to the sum of anti-clockwise moments about the same point. So for anti-clockwise, we have F. I will just swap the sides. So I will just say F. No, F is not clockwise, but I'll just swap them. So F times the perpendicular distance from the pivot, which is 1.1. So that is 1.10, should be equal to the sum of clockwise moments, which is, I'll start with 3 newtons. So it is 3.0 times the perpendicular distance from the pivot, which is this distance here. And this distance is 4 minus 1.10, which is going to be 2.9 meters. So this is going to be times 2.9 meters, then plus the weight of the beam, 44, and the perpendicular distance from the pivot is this one here, which will be 1.7 minus, it is 1.7 minus 1.1, which is 0.6 meters. So this is going to be 44 times 44.0 times 0.6 meters. So I'll just press my calculator. 3 times 2.9 plus 44 times 0.6 divide by 1.1. So this is giving me 31.909090. So it is approximately 32. So this is 32 newtons. So avoid writing an answer less than 2 significant figures unless it is exactly that answer. Then calculate the force exerted on the rod by the pivot. So this one is 32 newtons acting downwards. This is 44 downwards, 3 newtons downwards. So if there is a force acting on the pivot, it should be in the opposite direction. I'll call this force force P, upwards. So for equilibrium, the resultant moment should be 0 and the resultant force in any particular direction should be 0. So the sum of forces downwards should be equal to the sum of forces upwards. So I will say P. The force at P, or call it force P, is going to be the forces downward, 32 plus 44 plus 3. Those are the forces acting downwards. So 32 plus 44 plus 3, which gives us 79. The sphere in B is now immersed in a liquid in a container as shown in the figure. The density of the liquid is 1,100 kilograms per meters cubed. The upthrust acting on the sphere due to the liquid is 2.5 newtons. Use Archimedes' principle to determine the radius r of the sphere. Remember, this was 32. And remember, this distance has not changed. It was 1.1. This distance has remained 0.6. And this distance has remained 2.9. Use Archimedes' principle. So if you remember Archimedes' principle says that upthrust is equal to the weight of the liquid displaced. Upthrust equals the weight of the liquid displaced. And the upthrust, remember, was 2.5. And the weight of the liquid displaced is going to be mg, which is the same as density times volume, that is mass, then times g. So we shall simply say the upthrust is, and of course you remember volume, it is a sphere, so the volume of a sphere is 4 over 3 pi r cubed. So I'll simply say 2.5 equals to the mass, the density, which is 1100, times the volume, which volume is 4 pi r cubed over 3, then times g, which is 9.81. Okay, so I'm going to make r the subject, of course. So r is going to be 3, or 2.5 times 3 divided by 1100 times 9.81 times 4 pi, and this will be under the cube root, or I'll raise this to power 1 over 3. That is under the cube root. So I'll just press my calculator. 2.5 times 3 divided by 1100 times 9.81 times 4 pi. Then I find the cube root, which will be shift cube root of the answer, which is 0.038. So this is 0.038. Like I said, avoid writing any answer which is not exact to less than 2 significant figures. Calculate the magnitude and direction of the resultant moment of the forces on the rod about P. So we want the magnitude and the direction of the resultant moment of the forces on the rod about P. So first of all, let's find, of course, the weight has remained 3 newtons. There's tension, there's upthrust here, this is upthrust, which is 2.5 newtons. So the only force acting upwards here is the tension, and the tension is going to be 3 minus 2.5, which is 0.5 newtons. That is the tension in the rope. Let's check the magnitude and direction of the resultant moment. So I'll first start with anticlockwise moments. The sum of anticlockwise. So anticlockwise will remain with F. F is anticlockwise times this perpendicular distance. So it is equal to 2 times 1.1. That is anticlockwise. Then clockwise, the sum of, by the way, anticlockwise, we also have, let me see. Okay, so if the weight of 3 newtons is acting downwards and the upthrust is 2.5, it means the unbalanced force is only 0.5, which should be acting downwards. The unbalanced force acting downwards is 0.5 newtons, which is also causing a clockwise moment. So clockwise moments, we have the sum of clockwise. We shall have the weight of the rod, which is 44, times the perpendicular distance, which we got as 0.6, plus the unbalanced force, which is 0.5, because the upthrust reduces the resultant force on the right hand side. So it is 0.5 times the perpendicular distance, which is, I think it was 2.9. Okay, so then we can now find the resultant. Of course, I noticed that this is going to be bigger than this one, so I will say 32 times 1.1 minus 44 times 0.6 plus 0.5 times 2.9. So I'll press my calculator. 32 times 1.1 minus 44 times 0.6 plus 0.5 times 2.9. So this is giving me 7.35. So the resultant is 7.35, which is approximately 7.4, or just write 7.35 Newton meters. But note that the sum of clockwise moments is bigger than the sum of anticlockwise moments. I mean, the sum of anticlockwise moments is bigger than the sum of clockwise moments. So it means the direction of the resultant is going to be anticlockwise. If the answer was a negative, I would say the direction would be clockwise. Okay, so it is anticlockwise. Then define power. Of course, we know power is the rate of doing work. You could define power as work done over time taken. You could define power as the rate of transfer of energy. Rate of transfer of energy. Any of these. Now, in an exam, of course, you don't need to give the examiner alternatives. You just stick to one definition. Then a force F takes time t to move an object through a distance displacement x at a constant velocity v in the direction of the force. The work done by the force is W. Use the definition of power to show that the power P transferred by the force is given by power is equal to force over force times velocity. So since the work W is defined as, of course, we know the work W is defined as force times displacement. So the work W is equal to F times X. And we know that power is the rate of doing work. So it is W divided by T. So which means power is going to be Fx divided by T. And we also know that V, the speed, is equal to the displacement X, then divided by T. Hence, power is going to be F times V as required. A block is pulled up a slope by a wire attached to a motor as shown in the figure. The useful power output of the motor is 56 watts. This is useful. The block has a weight of 430 newtons and travels with a constant velocity along the slope at an angle of 11 degrees to the horizontal. Assume that there are no resistive forces opposing the motion of the block. Calculate the tension T in the wire. Now, they said it is moving with a constant velocity along the slope, which means the acceleration along the slope is 0, which means the resultant force F is going to be 0. So I have just to find the forces acting on this one. We have the weight. Of course, the weight acts vertically downwards. That is the weight, which is going to be M times G. So there must be a force which acts perpendicular to the surface, which is the component of the weight, which is going to be mg. Remember, this angle is going to be 11 degrees. So this is going to be mg cos of 11, which balances with the force acting upwards. And there will be a component of mg parallel to the plane, which is going to be mg sine of 11. So mg sine 11 balances the tension in this wire so that there is no resultant force along the plane. So we want to find T. So the tension T in the wire is simply going to be equal to mg sine of 11 downwards. So this will be mg, which is the weight. Mg is the weight, so it is going to be 430 sine of 11. And when I press my calculator, 430 sine 11, that is 82. So T is approximately 82 newtons to two significant figures. Then calculate the speed of the block. Of course, we know that the speed is going to be got from, of course, power is equal to force times velocity. So the speed is going to be equal to the power divided by the force. So this is going to be, what was the power? I think the power was 56. So the speed is going to be 56 divided by the velocity, the force, which we have got as 82. So 56 divided by 82, and that gives us 0.68 meters per second. The rate of increase of gravitational potential energy of the block is equal to the useful power output. The rate of increase of gravitational potential energy is equal to the useful power output. One of the reasons for this is that there is no work done against resistance. By considering the motion of the block, state another reason. Of course, there is no work done against resistance, and they also told us it was moving with a constant velocity, which means kinetic energy is constant if the velocity is constant. So the second reason would be that at constant velocity, there is no gain or loss in kinetic energy. So at constant velocity, there is no change in kinetic energy. There's no change in kinetic energy of the block. The motor has an efficiency of 80%. Calculate the time taken for an input energy of 1.2 kilojoules to be supplied to the motor. So the input energy is 1.8. We know that efficiency is equal to the power output divided by the power input. Of course, if you want to multiply this by 100. So the efficiency has been given by 80%, which is 0.8. So I'll say 0.8 is equal to the power output. Of course, the initial we had a power output of 56, but we didn't know the power input. So the power input is what we are going to find initially. So that is power input. So the power input here is going to be 56 divided by 0.8, which gives us 70 watts. Now we have the energy input as 1.2 kilojoules. The power input was 70 watts. Of course, we also know that power is the rate of transfer of energy. So power is equal to energy over time, which means the power input is equal to the energy input divided by time. So it means I will say the time is going to be equal to the energy input or input energy divided by input power input. So I just substitute. The input energy is 1.2 times 10 to the power of 3. And the power input, we have got it as 70 watts. So I'll just press my calculator. 1.2 exponent 3 divided by 70. So this is approximately 17 seconds. A spring is suspended from a fixed point at one end and a vertical force is applied to the other end as shown. Okay, we can see length F. The variation of the applied force F with the length L of the spring is shown. Determine the spring constant. Of course, we have a graph of F against L. So L, when there is no force, the length is 20, so this means this is the original length. When we add a force of 30 newtons, the length is 60. That means the extension is going to be 60 minus 20. So if you want to use K equals to F over X, then you must use X as 60 minus 40, or just find the gradient. So K is going to be equal to the gradient, which is simply going to be 30 minus 0 divided by 60 minus 20. Of course, this is in centimeters, so I'll say times 10 to the power of minus 2. And when I press my calculator, I have 30 divided by 60 minus 20, which is 40, exponent minus 2. So that is 75. Determine the elastic potential energy in the spring when the applied force F is 15 newtons. So, of course, we know that elastic potential energy is going to be the area under the graph. Because it's a graph of F against extension, then it is the area under the graph, or you can use a half Fx. Since we have already got K, you could also use a half Kx squared. So, but the applied force is 15 newtons. So I have to go back and check 15 newtons. So I think 1, 2, 3, 4, 5. So 15 is here, and this is 40. So it is either the area under this part here. So if I use area under the graph, it will be a half times that is 40 minus 20, which is 20. Then on the vertical we have 15. So I'll say a half times 15 on the vertical, then times 20, but remember it was in centimeters, so I'll say times 10 to the power of minus 2, which gives us 0.5 times 15 times 20 exponent minus 2. So that is 1.5. So it is 1.5. Alternatively, you can use a half Fx. So I'll use this part too. The answer is 1.5. I'll also try this, or a half times F, which is 15, times X. So of course, X will subtract 40 minus that, which is still 20 times 10 to the power of minus 2, which is still the same as the area under the graph. Or you could use a half. We got K as 75. Then X is 20 times 10 to the power of minus 2, but this is going to be squared, which I think gives us the same answer, 0.5 times 75, then times 20 exponent minus 2 squared, which is still the same. So the answer is the same. Question 5, I think this is waves. A horizontal string is stretched between two fixed points A and B. A vibrator is used to oscillate the string and produces an observable stationary wave. At one instant, the moving string is straight, as shown in the figure. The dots in the diagram represent the positions of the nodes on the string. So if these are the nodes, I can even draw something that I can understand easily. I will change the color for another one. Yeah, I think I can understand that easily. Okay, the wave on the string has a speed of 35 meters per second and a period of 0.04 seconds. Explain how the stationary wave is formed on the string. Of course, we know how a stationary wave is formed. We must have a progressive wave traveling from one side to another side, and then a reflected wave from the the other side to the opposite side, and the two waves must meet. And because they are now identical, when they superpose, they produce a stationary wave. So I'll simply say a wave traveling along the string from A to B, a wave or a progressive wave. A wave traveling along the string from A is reflected at B. Is reflected end at end B. The incident and reflected wave. The incident and reflected waves superpose or meet. Of course, they are now of the same kind because the reflected wave is perfectly identical to the incident. So I would say, and since they are traveling in opposite directions at the same speed, and since they are traveling at the same speed, but in opposite directions, a stationary wave is formed. Okay, but since they are traveling at the same speed but in opposite directions, a stationary wave is formed. Okay, I think I write my V poorly. On the figure, sketch a line to show a possible position of the string a quarter of a cycle later than the position shown in the diagram. So it means I made a mistake here, but anyway, let me first see which line will I rub off. So V, the speed, is equal to lambda times F, which is, since we have been given the period, so this is going to be lambda over T. So on the figure, sketch the line to show a possible position of the string a quarter of a cycle later than the position shown in the diagram. Okay, so I have to rub off this first. I will rub off these first. So at a quarter a cycle. So if t equals to 0, we had destructive interference. Then at t equals to a quarter of a cycle, a quarter of a period, it means a wave which is propagating to the left has moved a quarter of its wavelength, and a wave which is propagating to the right has also moved a quarter of its wavelength, which means they're actually 2 quarters apart. So it means if we started with the t equals to 0 and we had a destructive interference, then it means at t equals to a quarter a cycle, then we are going to have constructive interference because the wave which is propagating to the left will have moved a quarter of its cycle, and the wave which is propagating to the right will have moved a quarter of its cycle in the opposite direction. This would result into something like this. Okay, so that is constructive interference is going to occur after a quarter a cycle. We shall have constructive interference. If we had started with the constructive interference after a quarter a cycle, we would have destructive interference because the path difference between the two waves would be 180 degrees. So if we start with as destructive interference, then it means after a quarter cycle, the path difference, of course, the path difference, they are going to be 180. The two corresponding particles are going to be a half a cycle apart. But remember, we started with destructive interference, so we shall have reversal of phase. We shall have reversal of the wave. So this is what we are going to have after another quarter cycle. Of course, after another quarter cycle, again, we shall have a horizontal line, and after another quarter cycle, we shall have something on the top, which is in the opposite direction to the one I've just sketched. So this is going to be our sketch here. Okay, then determine the horizontal distance from A to B. Okay, so I was trying to determine the horizontal distance from A to B. So to find that distance, I need to first know the wavelength. So V is equal to lambda times F, which is lambda over T. So the wavelength is going to be equal to V times T. I think they gave us the speed here as 35, so it will be 35 times T, which is 0.04. So let's see, 35 times 0.04, which is 1.4. That is the wavelength. So distance AB, this is 1 cycle, 2 cycles and a half. So distance AB is 2 cycles and a half. Distance A to B is equal to 2.5 of a wavelength, which is the same as 2.5 times 1.4. So I'll multiply this by 2.5, and this gives me 3.5. So the answer here is going to be 3.5 meters. A particle on the string has a zero displacement at time t equals to 0. From time t equals to 0 to time t equals 0.6, the particle moves through a total distance of 72 millimeters. A particle on the string has zero displacement at t equals to 0. From time t equals to 0 to time t equals 0.6, the particle moves through a total distance of 72 millimeters. So I'll just sketch initially at t equals to 0, that's what we had. So I'm going to take a particle which has zero displacement here at time t equals to 0. So first of all, I have to find out how many cycles will the particle have moved in this time between t equals 0 to t equals 0.06. Remember, the period was 0.04 seconds. So the number of cycles is going to be the time, which is total time, which is 0.060, divided by the time for one cycle, which is 0.04 seconds. I think this is 1.5 cycles. So let me try to sketch 1.5 cycles, 1.5 cycles. So if it is, let's say it starts by moving vertically downwards. So it goes downwards, that is a quarter cycle. It comes back, that is half a cycle. It goes upwards, another quarter cycle. It goes downwards, that is now one cycle. So moving down, up, up, down. This is a quarter, another quarter, another quarter, another quarter. That is one cycle, but it is 1.5. So again, it continues down a quarter, another quarter. That is now half. So it is going down. So this is, remember, the amplitude is this vertical distance here. This is the amplitude. So how many times does it cover this amplitude here? So it has 1 downwards, 2 downwards, 3 upwards, 4, 5, and 6. So it means 6 times the amplitude should be equal to 72 millimeters. So 6 times the amplitude is equal to 72 millimeters. 6 times the amplitude, because there's a total distance the particle moves through is 72 millimeters. So 6 times the amplitude equals 72 millimeters. So what is the amplitude? The amplitude is going to be 72 divided by 6, which gives us, I think this is automatically 12. So this is going to be 12 millimeters. Okay, so that was waves. Electricity state Kirchhoff's first law. Many times we are confusing the first law with the second law. For the first law, the algebraic sum of currents at a junction is 0. You could say algebraic. Of currents at a junction is 0. The algebraic sum of currents at a junction is 0. Or you can lose, let's say, the sum. The word sum should be in your statement, the sum of currents into a junction should be equal to the sum of currents out of the junction. The sum of currents into a junction is equal to the sum of currents out of a junction. That is Kirchhoff's first law. A battery is connected to two resistors X and Y as shown in the figure. The resistance of X is greater than the resistance of Y. Okay, so I will say R of X is greater than R of Y. Set and explain which resistor dissipates more power. Of course, we know that power is equal to V squared over R. Because they have mentioned resistance and I can see the PD here. So, and they are in parallel, so it means they have the same PD. So I start by telling the examiner that the PD across X and Y are the same since they're in parallel. The PD across X and Y is the same since they are in parallel. Okay, that's number one. But we notice that resistance X is greater than resistance Y. We know that from power dissipated equals to V squared over R. And we know that resistance R for X is greater than R for Y. So the one with the greater value of R has less power. The one with the smaller value of R dissipates more power. So since Y has a smaller resistance, I'll simply tell the examiner that so Y dissipates more power. This part here is very important. And so Y dissipates more power. Because power is V squared over R. So Y dissipates more power. Okay. Two resistors are made of wires that have the same length. So L is the same. Both wires are made from the metal of the same resistance. So ρ is the same, L is the same. State and explain which resistor is made of wire with the larger cross-sectional area. They say the two resistors are made of wires of the same length. So first of all, we know that resistance is equal to rho L over cross-sectional area. And remember, the resistance of X is greater than the resistance of Y. So you notice that resistance is inversely proportional to cross-sectional area if rho and L are the same. Resistance is inversely proportional to cross-sectional area. So the one with the bigger resistance has a smaller cross-sectional area. So it means the question is which one is made of wire with a larger cross-sectional area. So the one with the smaller resistance is made of a wire with a larger cross-sectional area. So I will say, so Y has the larger cross-sectional area. Cross-sectional area since it has small resistance, or it has smaller resistance. So this statement, the formula for R is equal to rho L over A is the most important thing here. Okay. A battery of EMF 9 volts, negligible internal resistance, is connected in series with the light-dependent resistor and a fixed resistor of 1800 ohms as shown in the figure. The voltmeter is connected across the fixed resistor. The reading on the voltmeter is 5.4 volts. Calculate the current in the circuit. So the reading on the voltmeter is 5.4 volts. Okay. So we know that the current is equal to V over R according to Ohm's law. The V is 5.4 volts divided by R, which is 1800. So we just press the calculator. 5.4 divided by 1800, which is 3 times 10 to the power of minus 3. That is the current. Then calculate the resistance RL of the LDR. So we can just find the PD across RL. Remember, the current will be the same because they're in series. So the PD across this will be 9 minus 5.4 volts. So I'll say the PD across, calculate the resistance RL of so the PD across RL is going to be 9 minus 5.4. I think this is 3.6 volts. Then we want resistance RL, which will still be V over I. Remember, the current is the same because they are in series. So this will be 3.6 divided by 3 times 10 to the power of minus 3. So this is going to be the answer, 3.6 divided by the answer, which is 1200 ohms. The intensity of the light illuminating the LDR increases, which means RL decreases, because resistance of the LDR is inversely proportional to light intensity. By reference to the current in the circuit, state and explain the change, if any, to the voltmeter reading. So first of all, the resistance of the LDR decreases. So I would say resistance of the LDR decreases. And if the resistance decreases, it means total circuit resistance has decreased, so the current increases. Total resistance decreases, that is total resistance for the circuit decreases. And remember, from V is equal to IR, I is inversely proportional to R if V is constant. So total resistance decreases, current in the circuit increases. So if current in the circuit has increased, then remember the one resistor is fixed. 1800 is fixed and the current through it has increased. So it means the PD across 1800 has increased. So the reading of the voltmeter increases. So the current in the circuit increases, and from V is equal to IR, the current has increased. But remember, the fixed resistance is fixed, and the current has increased, so the V has increased. So the voltmeter reading increases. Okay, as simple as that. I think this is the last particle physics. An unstable nucleus AZ decays by emitting a beta minus particle. So let's write an equation. X AZ is giving us a beta minus. So I'll write a beta minus, which is 0, -1. Let's say the new nucleus formed is Y. Of course, beta minus is always accompanied by, this is a normal particle, it is always accompanied by an antiparticle, which is going to be an antineutrino. Let's balance this. So this will remain A, and this will be Z plus 1. To balance the equation, this will be Z plus 1. Okay. So determine quantitatively, meaning you state a number, determine quantitatively the changes, if any, in A and Z when X decays. So in Z, the change is 0. There's no change in the value of A. Then in Z, the change, you see I have said it is plus 1. So the change is plus 1. It is plus 1. Z increases by 1. Then in addition to beta minus particle, another lepton is emitted during the decay. State the name of the other lepton that is emitted. Of course, the electron which is emitted is the electron antineutrino. Electron antineutrino. A particle P is composed of an up quark, and by the way, this particle here is an electron antineutrino. The one which is this particle here is an electron antineutrino, which always accompanies by a normal particle, which is the electron or the beta minus. A particle P is composed of an up quark and a down antiquark. Calculate the charge Q of P in terms of E, where E is the elementary charge. Show your working. So we know that the up quark, the charge of an up quark is of course plus 2/3e, and the charge of anti-down is minus 1/3e, so anti-down is plus 1/3e. So total charge, which is called Q, is going to be up plus anti-up, which will be 2/3e plus 1/3e, which is of course 3e/3, which is 1e. So the answer here is going to be plus 1. Plus 1e. Particle P belongs to two classes or groups of particles. Say the names of these particles, these two classes. So particle P has an up quark, and it is made up of quarks, so that is automatically hadron. Because it's made up of quarks, it is automatically a hadron. Number 2, it is made up of a quark and an antiquark, so it is automatically meson. Okay, so I think that is the end of this paper. See you in the next paper. Bye bye.